Well, welcome back. This is Unit 6.2, and this is our section on stoichiometry, and this can be found in Chapter 12 of your textbook. Okay, so before we start, we need to talk about some subcategories of the 5 main types of reactions that we talked about in 6.1. And the first subcategory that we need to talk about is what's called a precipitation reaction. And a precipitation reaction, we look back earlier, like way earlier in the year. One of our indicators of a chemical reaction is that if a solid is produced. If a solid is produced from 2 liquids, then that is an indication that there is some kind of chemical reaction that's happening. Okay, and these solids are called precipitates, or it's a precipitation reaction. So a solid that is formed from 2 aqueous solutions is called a precipitation reaction. Now, how do we know a solid is formed? Well, if you look on your reference materials right beside the polyatomic ion list, you're going to see the solubility of common ion compounds in water. So what we're looking here is a double replacement reaction. So sometimes the state of this compound is given here in a chemical reaction, and sometimes it's not. Sometimes it's important for the reaction to know that, sometimes it's not. Well, in an ionic reaction between 2 ions, we can figure this out. Mostly. Okay, so here we have AgNO3. Okay, so if we look over here, the way you use this chart is it's broken up into 3 sections. Compounds that are always soluble, compounds that are soluble but have exceptions, and then compounds that are insoluble that have exceptions. Okay, so soluble means it dissolves in water. Insoluble means does not dissolve in water. So what we're looking for here, do these ions dissolve in water? Well, my first tip is on always soluble, get really familiar with these ions that are always soluble, because when you see them in a compound, no matter what, that compound is going to be soluble. Now, these are going to include the group 1 ions. So the one that has hydrogen in it. So group 1, the alkali metal ions, that's group 1. So any ion that's here in this group 1 is going to be always soluble, always soluble. Okay, so that includes lithium, sodium, potassium, rubidium, cesium, etc. Okay. Polyatomic ions that are always soluble are ammonium, nitrate, chlorate, chlorite, ClO3, ClO4, C2H3O2, which is the acetate, and then hydrogen carbonate, HCO3. Okay, so these polyatomic ions are always soluble. So if you recognize those right off the bat, you'll know that any compound that contains those is always soluble. Okay, so if it's not here, what you're going to do is look to see if it's soluble here with exceptions. So these are soluble unless, like chlorine is soluble, unless it's bonded to silver, lead, copper, or mercury. Fluorine is soluble unless or except in the case where it's calcium, strontium, barium, lead, or magnesium bonded to it. So that's how you use that. And then these are insoluble. So these are insoluble, the oxygen and the hydroxide, unless or except they're bonded to an alkali metal. See, alkali metal, that means it's going to be soluble. NH4, always soluble. And then these, calcium, strontium, and barium, those elements there. Okay, and these polyatomic ions right here are always insoluble unless they're bonded to an alkali metal or NH4. Okay, so that's how you read this chart. And the more you do it, the more it sinks in, the easier it is. So let's try it with these. So AgNO3. Well, we're looking at the ions. So Ag, silver ion and nitrate ion. And then these ions here. Okay, so first AgNO3. So if we look through here, we don't see silver here. We don't see silver here. And we don't see silver here. Now, we're not looking at the exceptions yet. We're just looking at the main part of it. Okay, the main parts. And I don't see silver there. So I'm just going to move on to nitrate. Okay, so let me erase this. Nitrate. Do you see nitrate? Well, if you look here in always soluble, you're going to see nitrate right here. So no matter what nitrate is bonded to, it's going to be soluble. Okay, so this compound is soluble. Now, you think it may be liquid, right? But liquid really is for if you're talking about an element. Like we could have liquid mercury. Mercury is liquid at room temperature, so that's when we would use L. If it's a compound that's liquid or soluble, that means it's soluble in water, okay? And so that's when we use the AQ. So we talked about the, oops, I wrote Q first. We talked about the abbreviations in 6.1 that we use in chemical equations. So AQ is aqueous. It means it's dissolved in water. So silver nitrate is dissolved in water. That's AQ. Okay, so let's go to the next one. Calcium chloride. Well, I don't see calcium here. I don't see calcium here, and I don't see calcium here. So let's go to the chlorine. I don't see chlorine here. There's chlorine right there. Okay, so chlorine is soluble unless or except when it's bonded to silver, lead, copper, mercury. So here it's bonded to calcium. So calcium is not an exception. So it is going to remain soluble. Okay, so I'm going to put an AQ here because that's aqueous. Now we're going to mix these together. So remember, when we mix these together, it's inside outside because this is a double replacement reaction. So we're going to bond these two. Let me change colors. And then we're going to bond these two. So that's how we get silver chloride here and then calcium nitrate here. Now remember, we don't bring over these subscripts. So we look at silver, that's a +1, chlorine's a -1. So that's the formula for silver chloride. And here we see calcium is a +2, nitrate's a -1. So in order to make this formula correct, we have to swap and drop. So that's why you see this 2 right here. Okay, so it's already been done for you when I wrote the equation out. All right, so we need to look and see if this is a precipitation reaction. So we're going to do this whole thing over again. Silver chloride. All right, so remember, chlorine is here. So it's soluble unless, except when it's bonded to silver. So there we see silver. So that's going to be a precipitate. So when we mix these two things together, that silver chloride is going to form a solid. So I'm going to put an S there, right? Okay, and let's check this one, calcium nitrate. All right, so if we remember, all nitrates are soluble, always. There's no exceptions to that. Okay, so this is going to be aqueous. All right, so when we take these two chemicals, silver nitrate and calcium chloride, both liquids, both aqueous. So let me draw a little picture here. Okay, so I have my silver nitrate in a beaker. Okay, and I'm going to pour that together with calcium chloride. Okay, it's in a beaker, it's aqueous. And I'm going to pour it into one beaker together, right? I'm going to mix them together. That's what this plus sign is, mix them together. I'm going to get down here in the bottom of this beaker, okay, it's going to form a solid. Okay, and down here in the bottom, you're going to see it's like powdery. This is going to be my solid silver chloride. Okay, and then up here in this solution, still dissolved in this liquid, is going to be my calcium nitrate. Okay? So that's what's happening. You're going to get a precipitate or a solid that forms. It's going to, of course, since its density is greater than this liquid, it's going to fall to the bottom, precipitate, okay, to the bottom of this beaker. And then we can pour this off onto filter paper into a funnel. We can filter that solid off and find out just how much silver chloride we got. Okay, so these are called precipitation reactions. And that's going to be important as we go on when you look at these, because sometimes it's going to ask you in some of your questions, how much of the precipitate are we going to get? Okay. All right. Okay. So again, to review just for a second, what is the unit that we use to measure quantities in chemistry? Now, I'm not talking grams, not grams. What's another way to measure quantities? And this is specific to chemistry. Okay. And we celebrated on October 23rd. What could it be? Do you know? Oh, let's look at the first letter. It starts with an M. Did you figure it out? Do you know what it is? Moles. Yeah, so if you said moles, moles are going to come back in now. We talked about them when we talked about converting moles, grams to moles, and then moles to either liters or moles to particles, Avogadro's number. Remember all that? All right. So moles are how we measure things in chemistry. All right, so let's look at this equation again. Now, here's our skeleton equation, okay? And we found out that we're going to have a precipitate here of silver chloride. So after we get the correct formulas, remember I said from here on out, every single time you see an equation, we're going to have it balanced. Because we can't really use this equation until we balance it. We can't answer questions about how much silver chloride we're going to get, how much calcium nitrate is going to be in the solution until we balance the equation. Okay, so let's go ahead and balance this equation. So let's start with silver here. We have one silver here, one silver on this side. Okay, so we're good with that. So nitrate, NO3. Okay, so I have nitrate on this side, so I'm going to balance this as a polyatomic ion. I'm going to keep it together and not split it up because I don't see any other nitrogens or oxygens over here. So I can keep it together. So we have one NO3 here, but we have two NO3 on this side. So we have to put a 2 here to balance out the nitrates. Now, that unbalanced our silver that we balanced first. So I have to backtrack. So we have 2 silvers here. So I'm going to have to make 2 silvers here. Okay, so now we have 2 silvers and 2 nitrates. So now we can move on to calcium. So calcium, we have 1 here. We have 1 here. So we're good. Chlorine, we have 2 chlorines here and then 2 chlorines here. So we're good. So now this equation is balanced. So now we can ask questions about this equation. All right, so a typical question might be, a student places 8 moles of chromium metal, which is Cr plus 3, with an excess of concentrated hydrochloric acid. How many moles of hydrogen gas are formed? All right, so in order to do this, we had to have an equation. So let's go ahead and write this out. So chromium plus 3, chromium metal, is placed in an excess of hydrochloric acid. So we're going to put it with hydrochloric acid, HCl. Okay. So what are the products of this? Well, this is what type of reaction? Single replacement. So is this chromium stronger than this hydrogen? Okay. And I'm going to answer that for you. The answer to that is yes. But you would look on your activity series, okay, to make sure. So chromium is going to kick out hydrogen, and we're going to get chromium chloride that's going to be produced. Okay, chromium chloride plus hydrogen gas. Okay, now remember, Hydrogen is kicked out as just the H, but it's a diatomic element, so we had to put that 2 there. All right, so now we need to make sure that this is a proper formula. We need to check our charges. So here we're told that it's chromium plus 3, and chromium is a transition metal, so it had to tell us the charge of chromium. There's no way to look at the periodic table and figure that out. So we have chromium that's plus 3. Chlorine is a -1. So in order to get a good formula, these don't cancel out to 0. We have to swap and drop. So this 3 is going to go down to there. So that is the correct formula for chromium chloride. Okay. All right. So now before we can do anything else, we have to balance this equation. Remember, you have to balance equations before you can answer any questions about them. 1 chromium here, 1 chromium here, 1 hydrogen here, 2 hydrogens here. So I need to put a 2 here to make 2 hydrogens. Okay, 2 chlorines here, 3 chlorines here. All right, so we need to make the chlorines equal. So in order to get them to equal, we had to find the least common multiple. And between 2 and 3, that's going to be 6. So how would I make 6 chlorines here? I would have to put a 2 there to make 6 chlorines. So over here, I have to change my coefficient here. Okay, and I had to make 6 chlorines. Well, there's no subscript, so I had to put a 6 here. So that unbalanced my hydrogen now that I had to backtrack and fix. So 6 hydrogen. So I need to put a 3 here to make 6 hydrogen here. And 2 chromiums, I had to backtrack and fix chromium. Okay, so now that I've backtracked and I think that I fixed everything, I don't want to move on until I make sure. So 2 chromiums, 2 chromiums, 6 hydrogen, 6 hydrogen, 6 chlorine, 2 times 3 is 6 chlorine. All right, so now we have a balanced equation. Now we can answer questions about this reaction. So it says here that the student places 8 moles of chromium with excess hydrochloric acid. So one thing that I want to tell you, again, before we move on, are these coefficients that you see in front of these compounds. We need 2 chromiums. Okay, so up to this point, we just have been saying we need 2 chromiums, but this really is an amount of chromium. All right, and so if we remember, amounts in chemistry are indicated as moles. So this is really 2 moles of chromium combined with 6 moles of hydrochloric acid will produce 2 moles of chromium chloride. Chromium 3 chloride actually is the name, and 3 moles of hydrogen gas. All right, so these coefficients are indicators of an amount in moles. Okay, all right, so let's go back to our question. We have 8 moles of chromium metal. So each time we go through this reaction, okay, it's called 1 mole of reaction. RXN is the abbreviation for reaction. So going through this reaction one time is called 1 mole of reaction. So in 1 mole of reaction, how many moles of chromium does it take? 2. Okay, so if we go through and use 2 moles, okay, oops, I didn't want to cross that out. I used 2 moles. That leaves 6 moles, right? So every time I go through this reaction, I use 2 moles of the 8. Okay, so I had 8. So if I use 2 moles of it, I have 6 moles left over. So I can go through this reaction again. Okay, so just let me put a 1 there. Another mole of reaction is going to use 2 moles of chromium. Okay, so 2 more. That's going to leave me 4. I'm going to go through this reaction again. 1 mole of reaction. It's going to use 2 more. So I have 2. So 1 mole of reaction. Okay, oops, mole of reaction. I'm going to use the rest, the other 2. So I can go through this reaction 4 times with the amount that I was given. I can go through the reaction 4 times. All right, so I'm going to write that over here. I can go through this reaction 4 times, 4 moles of reaction. Each time I go through this reaction, I'm producing 3 moles of hydrogen gas. So the first time I go, I'm going to produce 3. The second time I go through, I'm going to produce 3. The third time I go through, I'm going to produce 3. And then the fourth time I go through, I'm going to produce 3. So how many moles of hydrogen gas are formed? 3 plus 3 plus 3 plus 3 is equal to 12. So I'm going to form 12 moles of hydrogen gas. And we get that by looking at the balanced equation. This is called a ratio, right? For 2 moles of chromium, I'm going to produce 3 moles of hydrogen gas. Now, if we think about this right here as an equal sign, we can see that 2 moles of chromium is going to equal 3 moles of hydrogen gas. Okay, this is called stoichiometry. That's all it is. It's a word that sounds hard, fancy, complicated, but it's really not. You're just using a balanced chemical equation to find out how much of something is needed or produced. Okay, so if I had another question that said, if I have 8 moles of chromium, how many moles of hydrochloric acid are going to be used if this uses all of these 8 moles? Well, we know we can go through the reaction 4 times, so 4 times 6 is 24 moles of hydrochloric acid are needed. Okay, now it says we have an excess of concentrated hydrochloric acid. So what this means is we have more than we're ever going to need. So let's say we were given 100 moles. Okay, let's say we're given 100 moles of hydrochloric acid. How much is going to be left over? Well, if we go through the reaction 4 times, we're going to use 24 moles of it. If we had 100, that means that we had 76 moles in excess. Okay. All right. So what's limiting this reaction? You may see that term thrown around as well. Limiting reagent, or what's limiting the amount of stuff we can get in this reaction? Well, that would be the chromium. Because we only had 8 moles of chromium, okay, we had 100 moles of hydrochloric acid. What are we going to run out of first? We're going to run out of chromium first. Okay, we're going to have 76 moles of hydrochloric acid left over. So if we decided to put more chromium into this beaker, then we'd have the reaction go again because we had leftover hydrochloric acid. Okay, that's like making a sandwich. If you're going to make a grilled cheese sandwich, you need 2 pieces of bread and 1 slice of cheese, right? So if you had 2 slices of bread and 10 slices of cheese, how many sandwiches could you make? Well, you could only make 1 sandwich because you only had 2 slices of bread. It doesn't matter how much cheese you had. So you're going to have 9 slices of cheese left over, right? But if you had 2 slices of cheese and a whole loaf of bread, there's like 20 slices in a loaf of bread? But you had 2 slices of cheese, well, you can only make 4 sandwiches. So you're only going to use, you can make 2 sandwiches. So you're only going to use 4 slices of bread. So you'd have 16 slices of bread left over. Your cheese there is your limiting reagent. Okay, so these are all kinds of questions that you may see on your problem sheet when we get to that. Okay, but using these coefficients, these molar ratios, to answer questions about a reaction is what's called stoichiometry, those ratios. All right. So if we take the balanced equation that we looked at for the ratios of chromium metal to hydrogen, we can use math to help us calculate the proper amount of gas that's going to be produced. And sometimes this is really easy and really logical because we're given a whole number like 8 moles, right? But What if we weren't given 8 moles? What if we were given something like 8.37 moles? Okay. So what we just did in our head back here on this previous question, okay, this stoichiometry, this was a dimensional analysis problem. That's just like me saying, we're really familiar with time. How many minutes are in an hour? Well, we know that 60 minutes are in an hour, right? So that's really dimensional analysis. We're converting units, minutes, from hours. So this really is the same thing. So remember, the purpose of dimensional analysis is to change from one unit to another unit. So in this previous question, we're changing from moles of chromium to moles of hydrogen. So it's just really a dimensional analysis problem, okay? But it was easy because we used whole numbers, right? We started with 8, but it takes 2 each time. So if it takes 2 each time, we saw that it took 4 moles of reaction. And each time we do, we get 3. So 4 times 3 is 12. That was easy. But now we have 8.37 moles, okay? So that's not going to be so easy because 2 doesn't go into 8.37 evenly. But we can use our concept of dimensional analysis to help us solve this problem. Okay, so remember the steps of dimensional analysis. And if you do remember those steps, like I've asked you to remember, then this gets really, really easy. So we're going to start off with our given 8.37 moles of what? Chromium metal over 1. Okay, so start off with your given over 1. And then it's just a matter of answering those questions. So I'm going to put a line here. Question number 1, what unit do I want to get rid of? Well, we're asking for moles of hydrogen as our answer. How many moles of hydrogen gas are going to be produced? So we want to get rid of our moles of chromium. So I'm going to put it on bottom here so it can cancel. What are we converting it to? Moles of hydrogen. So that's going to go on top. Okay. So remember I said if we look at our equation, this arrow here really means equal. And what is a conversion factor? Something that's equal to something else, like 60 minutes is equal to 1 hour. So here, 2 moles of chromium is equal to 3 moles of hydrogen. So 2 moles of chromium is equal to 3 moles of hydrogen. Okay, so there's our conversion factor. Okay, what can we cancel? Moles of chromium. So what are we left with? Our unit, moles of hydrogen. Is that what we want? Yes, moles of hydrogen. Okay, so we can use this concept of dimensional analysis to help us figure this out. So if we take and do this math now, remember for this math, it's this times this, okay, divided by this times this. So it's 8.37 times 3. Okay, so let me turn on my calculator here. 8.37 times 3 is equal to 25.11 divided by 2 times 1 is 2. Okay, so I'm going to divide that by 2. I'm going to get 12.555 moles of hydrogen. Okay, because that is the unit that's left over right here. Moles of hydrogen is the unit that we didn't cross out. So that's our unit for our answer. Well, let's look. How many sig figs here? We have 3 sig figs. So our answer can only have 3 sig figs. Here's 1, 2, 3. So we're going to look at this 5 right here to see if we round. Okay, so 5 does round this up. So it's going to be 12.6 moles of hydrogen as our final answer. Okay, that's stoichiometry. That's as easy as it is. So it sounds hard, but it's really, really easy. Okay. All right. So variations on a theme. What does that mean? Well, it's been pretty basic up to this point, but hey, we're using moles, right? 4 months ago, You'd never heard of the word moles. And then now look at all you've learned. So what if we were given the amount of chromium in grams instead of moles? And we're asked for an amount of hydrogen in liters because, gas, we know from our unit on gases now, gas is measured in liters. Can we do that? Okay, so let's say we had 452 grams of chromium. Can you think of a way that we can take this grams of chromium and get liters of hydrogen? Can you map that out? Well, if you said to use the mole map, you are 100% correct. So remember, when I introduced the mole, we were converting from grams to moles, okay? And, didn't write the L, moles to particles, right? And then grams to moles to volume, okay, or liters. We use the mole map, right? We can go from grams to moles using molar mass. We can go from moles to particles using Avogadro's number. And we can go from moles to liters using 22.4 liters. Now, this is only for gas. This isn't liquid, okay? This is, remember, only for gases, okay? If we were going from liquid, we would need the density, okay? The molar volume of the compound, all right? All right, so since hydrogen is a gas and we're given grams here, we can take grams to moles and moles to volume. Really, really simple. All right, so let's look at this. So here's our given. Okay, let's go back and grab our equation. So this is going to be 2 to 6 to 2 to 3. So let's actually just let me erase this. We'll have our equation here. We'll just come back to our equation when we need to use it. Oops, went the wrong way. All right, so let's say that we're starting now with 452 grams of chromium. Okay, we're going to put that over 1. All right, so let's start asking our questions. What unit do we want to get rid of? Grams of chromium. Okay, and what do we want to convert it to? Well, looking at our mole map, we want to convert it to moles. Moles of chromium. You want to convert everything to moles because remember, moles is that central hub. Everything is connected to moles. Grams is connected to moles. Particles is connected to moles, and liters is connected to moles. So that central unit for all of them right here is moles. So no matter what kind of problem you have, and I may have said this in the past, if you don't know how to do this, then the first step, convert everything to moles. Okay. Now, once it's in moles, you may still not know what to do, but that may trigger some memory and go, oh yeah, I can do moles. Okay, so convert everything to moles all the time. Even if you don't know what to do, convert it to moles. And that may give you a clue. All right, so 1 mole of chromium is how many grams? Well, we need to look at our periodic table for that. Okay, so let me pull out my periodic table here, and I think it's 52 or 55. Okay, so it's 52. All right, so 1 mole of chromium is 52.00 grams of chromium. All right, cancel what you can cancel. So I can cancel grams of chromium. Well, what unit do I have left? Moles of chromium. Okay, so am I to my answer? No, because I want liters of hydrogen. So I need to do another conversion factor. So we start out back at question number 1. Okay, in these questions, if you had not been in my class, like you moved in from another school or you moved from remote to in-person, the reference materials that I gave you, this is what I'm referring to when I'm referring to the steps. So look on those reference materials and find that section that says steps for doing a conversion. Okay, so here are the reference materials. Here's the rules for sig figs, and we are counting sig figs. So let's see, how do I go to the next page? Oh, right here. All right, there's the periodic table. Here's the other page. Here's the mole map right here. So we're using the mole map here, and conversions right here. Steps for the conversion. Start with you given over 1, and here are the steps right there. So that's what I'm referring to when I'm talking about, what do I want to get rid of? Where can I put that unit so it cross cancels, et cetera, et cetera. What can I cancel, et cetera. All right, so going back to our problem. So moles of chromium is what I want to get rid of. So where can I put it so that it cross cancels? In the bottom here, because it needs to be opposite. And what do I want to convert it to? Well, if we look at our mole map, and if we look at our equation, remember, we're at the wrong way again. 2 moles of chromium is equal to 3 moles of hydrogen. So once you get it into moles, this is where we're going to do the conversion to a different unit. So I want to convert this to moles of hydrogen. So looking at our equation, we need 2 moles of chromium is equal to 3 moles of hydrogen. So 2 moles of chromium is equal to 3 moles of hydrogen. Okay, cancel what you can cancel. So now we're in moles of hydrogen. Is that what I want for my answer? No. So we have to do another conversion factor. Okay, start back with question number 1. What unit do we want to get rid of? Moles of hydrogen. Where do I put it? Cross-canceling, opposite of where it is, so on the bottom here. So what do we want to convert this to? We want to know liters of hydrogen. So can we go from moles to liters? Well, look on your mole map. Moles is here in the center, and liters is connected to it. So we can go from moles to liters. So I'm going to put liters of hydrogen here. Okay. What is this equivalent? 1 mole of gas is equal to 22.4 liters. So I'm going to put 22.4 liters. These are equivalents. What can I cancel? Moles of hydrogen. Oops, I forgot my 2 there. All right, so now I have liters of hydrogen. That's what I want for my answer. So all I have to do is the math now. This is reaction stoichiometry. Okay, reaction stoichiometry. That's all this is. So I do 452 times 1 times 3 times 22.4. Okay, so let's grab your calculators. Okay, so 452 times 3 times 22.4. Okay, and all that's going to be divided by 52 times 2. Okay, and so that's going to give me 292.0615. Okay, and this is all calculator vomit. This is really not our answer because our original data was 3 sig figs. Okay, so our answer can only be 3 sig figs, 292, 1, 2, 3. Okay, so we look at the 0. That's calculator vomit. It doesn't matter. Does the 0 round this? The answer is no. So we get 292 liters of hydrogen gas is our answer. So for this reaction, if we're given 452 grams of chromium metal and we had excess hydrochloric acid, like all the hydrochloric acid we're going to need, we can produce 292 liters of hydrogen. Okay, reaction stoichiometry. That's all this is. Okay, now you can ask a lot of questions about that one reaction, okay, and about this amount of chromium. Like I could ask you, if I'm given 452 grams of chromium, how much hydrochloric acid will I need to complete this reaction? Okay, you're going to do the same thing up to this point. So we're not worried or interested in moles of hydrogen now. What would we be interested in? Okay, so let me just take this out. And this is going to go. What would we be interested in? Hydrochloric acid, right? Let me just clean this up more. Okay. So moles of chromium. Okay. We are interested in the hydrochloric acid. So let's look back. 6 moles of hydrochloric acid is needed for 2 moles of chromium. So 2 moles of chromium is going to require 6 moles of hydrochloric acid. Okay. So here, and we couldn't ask about we couldn't ask about liters of hydrochloric acid because hydrochloric acid is a liquid, but we could ask about grams of hydrochloric acid. How many grams of that are we going to need? Well, chromium still cancels. So here we have moles of hydrochloric acid. So we'd use moles of hydrochloric acid here to grams of hydrochloric acid. Okay. 1 mole of hydrochloric acid is how many grams? Well, and we'd have to get the molar mass. Okay. So chlorine is 35.45. Okay. And we only have 1 of them. Hydrogen is 1.01. We only have 1 of them. So this is what? 36.46. So we put 36.46 here. Okay. Moles cancels, and now you have grams of hydrochloric acid. Okay. We could also ask, if you have 452 grams of chromium, how many grams of chromium chloride could you produce? So we could ask a lot of questions, and the only thing that's going to change is this right here. Okay. And of course, everything else after it, because the molar mass of chromium chloride is different than the molar mass of hydrochloric acid. Okay. But this is the key right here. Reaction stoichiometry, the ratio, mole to mole ratio, molar ratio from the equation. All right. That's it. That's all that stoichiometry is. So make sure you slap that like button right across the face. Give me a thumbs up and leave me a comment.